MSP-MVS is a novel multi-view stereo (MVS) method that targets the reconstruction of textureless areas. Traditional MVS methods struggle to accurately reconstruct these areas due to the lack of reliable pixel correspondences. To address this, MSP-MVS employs multi-granularity segmentation prior guided patch deformation, leveraging the recently proposed semantic SAM segmentation to extract multi-granularity depth edges. These edges are then integrated as a prior to restrict patch deformation within homogeneous areas. The proposed method first extracts multi-granularity depth edges using semantic SAM segmentation and then integrates them as a prior to guide patch deformation. This prior ensures that patch deformation occurs within homogeneous areas, reducing the potential for reconstruction failure. To further enhance the reliability of anchor selection, an anchor equidistribution strategy is introduced to equip patches with more uniformly distributed anchors, ensuring comprehensive coverage of their own homogeneous areas. However, the increased number of anchors raises computational loads and reduces time efficiency. To address this, iterative local search (ILS) optimization is proposed to represent larger patches with sparse representative candidates, significantly enhancing the expressive capacity of each patch. The state-of-the-art results on ETH3D and Tanks Temples benchmarks demonstrate the effectiveness and robust generalization ability of MSP-MVS. In contrast to traditional patch deformation methods, such as APD-MVS, which may erroneously cross depth edges and select anchors from heterogeneous areas, MSP-MVS leverages multi-granularity depth edges to constrain anchor selection within homogeneous areas. The proposed method also differs from learning-based methods, which often struggle with generalization and require complex and time-consuming post-processing. The authors highlight that their contributions include 1. Extracting multi-granularity depth edges and integrating them as a prior to guide patch deformation within homogeneous areas. 2. Introducing anchor equidistribution to ensure comprehensive coverage of homogeneous areas. And 3. Employing ILS optimization to enhance the expressive capacity of each patch. In the proposed MSP-MVS method, the pipeline begins with multi-granularity segmentation using semantic SAM, which generates 3 masks of varying granularities from coarse to fine. These masks are then used to derive boundary maps that capture semantic information at different levels: scene, instance, and feature. The aggregated segmentation map is obtained by retaining reliable masks that maximize the quantity of optimal distribution among internal pixels. This map serves as a new constraint to form a new anchor collection for patch deformation, enhancing the robustness of the deformation process. To address issues such as edge blurring and overlapping in panoramic segmentation, an edge correction strategy based on the conditional random field (CRF) algorithm is developed. The CRF model consists of unary and pairwise potentials, where the unary potential represents the probability of a pixel being assigned to a label, and the pairwise potential describes the joint probability of 2 adjacent pixels being categorized to specific labels. By incorporating both geometric and color similarities, the pairwise potential is defined as a function of depth and color differences between pixels, with the compatibility function micro defined in Zhu et al. 2023. As the estimated depth maps gradually become more reliable during iterations, the algorithm adaptively adjusts the pairwise potential to refine the edge correction process. The deformable patch matching cost is calculated as a weighted sum of the cost within the patch and the cost of the deformed patch. To ensure anchors are within homogeneous areas, they are classified into different subsets based on their intersection with boundary maps. The optimal distribution is determined by maximizing the number of preserved anchors and their proportion in each subset. By merging different mask maps and applying CRF for edge correction, MSP-MVS improves upon the baseline APD-MVS method by enhancing the coherence and clarity of depth edges, leading to more accurate depth estimation in multi-view stereo. The paper presents a novel approach to multi-view stereo (MVS) depth estimation, focusing on improving the accuracy and efficiency of the patch matching process. It introduces 2 key innovations: anchor equidistribution and iterative local search optimization. Anchor equidistribution aims to evenly distribute sectors within their own homogeneous areas, selecting multiple anchors per sector to avoid memory inefficiency and enhance the reliability of anchor selection. This method ensures a balanced division of regions without wastage. Iterative local search optimization is designed to identify sparse reliable candidates to represent each anchor patch, effectively broadening their receptive field. The optimization process involves categorizing candidates into 3 types based on their characteristics and uses an ILS function to minimize cost and maximum variance of profile. After several iterations, the optimal candidates and global optimal estimation can be identified. The proposed method, MSP-MVS, is evaluated on the ETH3D and Tanks Temples benchmarks, and compared against learning-based methods such as PatchMatchNet, ITER-MVS-LS, MVS-TER, EPP-MVS-NET, EPNET, and traditional methods like PCF-MVS, ACMM, and ACMMP. Quantitative results show that MSP-MVS achieves the highest F1 and completeness scores on both datasets, demonstrating its effectiveness in enhancing the accuracy and efficiency of MVS depth estimation. MSP-MVS, a novel multi-view stereo method, leverages multi-granularity segmentation prior to constraint patch deformation within homogeneous areas. This approach uses semantic SAM for extracting multi-granularity depth edges, which are then aggregated and corrected for accurate patch deformation. The state-of-the-art results on the ETH3D and Tanks Temples benchmarks validate the effectiveness of MSP-MVS. The proposed method introduces anchor equidistribution to offer patch more uniformly distributed anchors, enhancing the efficiency of the reconstruction process. Moreover, it presents ILS optimization to represent patches with sparse representative candidates, further improving the accuracy and efficiency of the method. Quantitative results on the ETH3D and TNT datasets show that MSP-MVS achieves the highest F1 score and completeness, demonstrating its superior performance and strong generalization capability. It also achieves comparative runtime compared to SOTA methods like APD-MVS and HPM-MVS. Ablation studies on the ETH3D benchmark validate each proposed component's effectiveness. Removing the multi-granularity SAM prior, anchor clustering, and edge correction leads to a decrease in performance, indicating that all components contribute significantly to the overall method. Future work includes leveraging semantic SAM to extract various 3D instances from point clouds, thereby facilitating object-level scene editing and improving scene interactivity. The paper also provides a comprehensive review of related works in multi-view stereo reconstruction, including patch-match, pyramid multi-view stereo with local consistency, and efficient edge-preserving multi-view stereo. In the realm of multi-view stereo, MVS, and autonomous driving, numerous research efforts have been dedicated to enhancing the accuracy and efficiency of depth estimation from various viewpoints. This summary combines insights from several key papers in the field, highlighting advancements in MVS techniques, their applications, and the challenges they face. The paper by Wei et al., 2023, introduces Surround OCC, a novel approach for predicting 3D occupancy in autonomous driving scenarios using multi-camera setups. It leverages geometric constraints and photometric cues to achieve state-of-the-art results on the KITTI dataset. Similarly, Wei et al., 2021, propose RMVS-NET, which adapts to different scenes through adaptive aggregation and recurrent refinement. This model significantly improves depth estimation accuracy in diverse environments. Xu et al., 2022, focus on geometric consistency and planar prior assistance in MVS, demonstrating improved performance over previous methods. Their work builds upon earlier research, Xu and Dao, 2019, that emphasized the importance of multi-scale geometric consistency for enhancing MVS accuracy. Zhang et al., 2023, revisit the representation of MVS-NET, introducing a region-aware approach that better handles textureless regions and improves overall depth estimation. Meanwhile, Zhang et al., 2023, introduced GeoMVS-NET, a geometry perception-based MVS method that outperforms existing techniques on various benchmarks. Other notable contributions include the work of Yuan et al., 2020, who developed dense hybrid recurrent multi-view stereo net with dynamic consistency checking, and Yao et al. 2018, 2020, who introduced MVS-Net and its large-scale dataset blended MVS for generalized MVS networks. Yu and Gao, 2020, proposed fast MVS-Net, which utilizes sparse-to-dense propagation and Gauss-Newton refinement for efficient and accurate depth estimation. Furthermore, Yuan et al. 2024a, 2024b, explore segmentation-driven deformation MVS with spherical refinement and M-optimization, as well as textureless aware segmentation and correlative refinement guided MVS. These approaches aim to address challenges such as textureless regions and varying lighting conditions. Lastly, Zhu et al. 2023 discuss the use of embedded conditional random fields for semantic segmentation, aiming to mitigate class-weight confusion caused by boundary effects. Zhu et al. 2021 also reviewed 3D-printed multifunctional materials enabled by AI-assisted fabrication technologies, highlighting the potential for such innovations in various fields. In conclusion, these papers collectively contribute to the advancement of MVS techniques, addressing various challenges and limitations in the field. They demonstrate the importance of geometric consistency, adaptive aggregation, region awareness, and geometry perception in enhancing the accuracy and efficiency of depth estimation from multiple viewpoints.